First, let's address your biggest concern. You were asking me to clarify how action potential works. So, firstly, one of the things that you had wrong is that information comes in at the dendrite, which hopefully you can see in my cursor. It is these little guys right here. Uh, on the left side of the neuron. They look like little trees. Information comes in there instead of the axon. Next, you almost had this right, but action potential is a positive shift instead of a negative shift. Because when action potential happens, a neuron's membrane potential starts at negative 70 millivolts. Then, as action potential continues, the membrane potential shifts to positive 50 millivolts. Now, for the actual steps of the action potential, I feel like you understand the concept, but you have some names mixed up. First, when the when the threshold of excitation is reached, the sodium channels, which are in blue, open. These guys are in blue, and they when they open, they allow sodium to flow into the cell. Oops. They allow sodium to get into the cell. This causes depolarization once sodium has entered the cell. Next, this causes the membrane potential to reach positive 50 millivolts. It started at negative 70, but now we are at positive 50. The next, once positive 50 millivolts has been reached, the sodium channels flows back up. Excuse my artistry. I know this is a Picasso, but it gets the point across. Next, once positive 50 millivolts has been reached, the sodium channels close, but the potassium channels open. Those potassium channels open, which causes potassium to leave the cell. Okay, so potassium has, oops, that's in red. Which this causes potassium to leave the cell once those potassium gates open. And that is called repolarization. As more and more potassium ions leave the cell becomes hyperpolarized, reaching negative 90 millivolts, which is less than you know, its resting potential. This hyperpolarization maintains itself for a little bit until it eventually reaches, well, it's not really working, until it reaches negative 70 millivolts again. This happens over and over again down the axon, so left to right, until it reaches these little guys called uh, the axon terminal. I hope you can see this, my cursor. Was I? Oh yeah, it goes all the way down to the all the way down the axon until it reaches the axon terminal, which is these little guys at the very end of the axon on the right side. So it goes left to right. Once at the axon terminal, synaptic vesicles, like what you had, like you got that down. You know what synaptic vesicles are. Synaptic vesicles fire neurotransmitters over the synaptic cleft, which is the space between neurons. And neurons don't touch each other. There's a space called the synaptic cleft in between them. And once the neurotransmitters cross the synaptic cleft, they bind to what is called the postsynaptic neuron, which is the spine of the dendrite of the next neuron. So I'll draw it for you. Just use your imagination. You see how the neurons don't actually touch? Because there's that synaptic cleft, the neurotransmitters travel over the synaptic cleft and they bind to the spine of these dendrites, which is also called the spine of the dendrite is also called the postsynaptic neuron. And then the cycle continues again all the way on the next neuron, and then over and over and over again. Okay, hopefully that makes sense. Next, I feel like I need to provide some additional clarification about the occipital lobe and the temporal lobe. You have them reversed. The occipital lobe controls vision, and the temporal lobe controls hearing. So just flip those around, and you're good. Lastly, you're asking about the difference between the motor cortex and the sensory motor strip. The main difference between them is that the motor cortex coordinates movements, while the somatosensory strip processes sensations. I hope this helps.